Welcome everyone. This is our fourth lab for our this is our lab 4. I know we have a makeup lab in the middle, so this is probably the fifth one, but that's fine. So today we'll talk about correlation and simple linear regression in R. And if we have time, then we'll get to multiple linear regression as well. But now I expect that you guys are like pros in R, so so hopefully we'll be able to move more quickly. Did you guys get this file? It's our lab for the RMD file. You can do a thumbs up sign or you can unmute yourself to speak. That would be helpful. There was this file of us in class, so I'm hoping that we can all leave our mics muted if you will, and we can respond more quickly so that we can go through it. So do we have this file?
No, not me. I don't.
Okay, let me paste it in the chat then. Okay, so that's the R lab 4. There might be some data sets that we need. So this would be the follow-up data sets and then post as well. Something that's a kind of form. So if we need any additional data sets, I'll post that for you too so that you can easily download it from here. So if you open that, the first thing is that we'll clear the workspace, okay? Which is what we've been doing the whole time, so that's familiar. And then the second thing we'll do is this set working directory. You can use a chunk of code, or we can use the click here to set working directory, and choose which directory we want to set it to. I won't go through all that because we already did. We already are familiar with that. So I'll just set working directory, and then I'll read the file. So it's BP follow-up data. And basically what we're hoping to do here, if you see when I open this data set, we have two variables. We have blood pressure at week 0 and blood pressure at week 24. So the idea is that you're looking at patients who have had their blood pressure measured twice, at baseline and 12 weeks after. And we can do a correlation. If you remember, we said that correlation is a way for us to assess the extent to which two variables, two continuous variables are related to each other. And so we have the correlation, and we have the data set. And so with that data set, first of all, we could look at the data set, but already opened it, so we don't need to go through that step anymore. Then we can visualize the data. Does everybody have their code open now? And can I keep going? Or should I slow down?
So I think your headset is the problem. That noise I told you about earlier is still.
But you can hear like a background noise, or what can you hear?
Yeah.
Okay. How about now? Is it better?
Yes.
Okay. All right. So yeah. Okay. Okay, so basically the first thing we can do, so first of all, Maimuna, do you have the file open?
Trying to open it, but we can go on.
All right. I think Glory just joined. Dr. Chieloka, do you have the file open?
Yes, I have it open.
You have it open. Excellent. Okay. All right. So if at any point in time you want to share your screen, please let me know so that I think it will be helpful to everybody to, if multiple people share their screen, we can assess the extent of engagement and have everybody participating along. One of the things we wanted to show you today is ggplot. I don't know if we've seen this in previous lab sessions, I don't recall. But ggplot is one of the most commonly used packages in R. You know, it's so versatile. You can use it to do multiple things, right? Like multiple plots, multiple charts. No, so it's not as if you can use it for other analysis, but it's mostly for visualization. It's very flexible, you know. So it's the same ggplot2 package. So hopefully you already have this installed because I think we have seen this before in previous labs. But today, what we want to do is use this to show you how a scatter plot would look like. I think we've seen scatter plots before. If, you know, depending on how, like, what the correlation is. And I think we've also seen this in class, where different scatter plots will tell you, like, what the, you know, depending on how the points are arranged on the plot, give you an idea of what the correlation is likely to be. Of course, this is just a ballpark. It's not like a firm number or this, or where you can say, this is for sure, this is the correlation that we're looking at, but this gives you an idea. So if you look at the correlation that sort of goes from this angle to this angle, you're looking at a near perfect correlation. So if you ask me to guess what the correlation for this is, so where you're looking at the correlation of the systolic blood pressure at week 0 versus systolic blood pressure at week 24, this is almost 1, you know, maybe 0.95 and 0.96, I don't know, and we can check in a moment. But you can use ggplot to create this scatter plot. And so with ggplot, the first character that you input here, this is the data. And then this is the Aes function. The Aes function is where you specify what the aesthetics are. Aes stands for aesthetics. You know, like it tells, like, okay, so this is the variables that you're going to input, X and Y. And then you specify what kind of plot you want. Here in this case is a geom point, where these are the different points in the you know, because the points that make up the scatter plot, and then you can use the labs function to specify the labels, you know, those labels that we have on the x-axis and on the y-axis. Okay, but if you want to see what the correlation looks like, then okay, so it looks like I'm very wrong, and that's surprising. So it says that the correlation here is 0.41. So I guess I'm very wrong then, because this is y, these are y. So if we had numbers that were more closely aligned around this, then that would have been a more perfect correlation. But this is a 0.41 correlation. Okay. Do we have any questions? Any questions at this point? Does anybody have? So there's many different types of correlations that you will see in statistics, but this is the most common, the Pearson correlation. And the Pearson correlation uses for continuous variables, and it essentially correlates the actual values of one variable to the next. But there are other types of correlation, like the Spearman, for instance, that does a ranking. It essentially does like correlation of the ranking of one variable to the ranking of the next. You know, like, and the Spearman correlation has value in certain statistics, but that's not what we're using here. We're using the Pearson correlation, which is the more commonly seen correlation statistic. Okay. And this is the code for it. COR, X variable, which is just one of the variables, doesn't matter which one, and then the method. All right, so example 7, which is basically where you ask 187 resident doctors about the hours worked and the GHQ score. We know that the GHQ score is a metric of mental health, and then you assess the extent to which both were correlated. So I want somebody else to share their screen and walk us through this example. Its correlation is fairly straightforward, it's simple, and we already have the code. Anyone want to volunteer? So I'm going to paste the data set in the chat. So the resident doctors.csv data set in the chat. Okay. Does anyone have questions, or do you want to share your screen so we can move forward?
Yeah, both.
Yes, Johnny.
I can't see the things you're sharing on the chat. Maybe probably because I'm joining with my phone.
You can't see anything in the chat?
Yes.
General, I can't see it too.
Oh, that's strange. So I shared files. You can't see the files.
Yeah, maybe because I joined from the phone.
Yeah, I just reshared. It's just files, like CSV files.
Which of the files? Because I went to the mail to.
Yeah, it's the resident doctors.csv, and then there's the BPFUFP, which is basically blood pressure follow-up.csv. If you look at the email, these files are also in the email, and we had shared them from there. Okay. All right. Yeah. So let us know how, if you're able to find the files, then the data sets folder that we shared via email. All right, so basically in this example, so let me run this code. Remember, this is the library that helps us to pull the Excel data set, and this is the call for the data set read_CSV. Now we have the data set here, 161 observations, and we can look at what the data set looks like. This is the first six observations in the data set. So we have age, we have mental health score, which is the GHQ score that we're looking at, that we're interested in. There's the job satisfaction score, the workload score, and there's an age category variable that's already created. Okay, and we can plot. You can do a scatter plot as well of the variables that we're interested in, which is the hours work and the mental health score. Okay. Okay, all right. So who can tell me what they think about this? So I just realized that I didn't allow sharing options. So I've allowed sharing options. So if anybody wants to share their screen next week, they should be able to. So let's talk about this plot. What do you think about this plot?
There's no correlation.
There's no correlation, yes. Why do you think there's no correlation?
Because if you look at it from the left to right, the variables are more like pointing upward intermittently. And then they appeared crowded at the extreme right.
Right. So you don't see like a clear pattern, just all over.
Yes.
Yeah.
Yes.
Yeah. But what do you notice about the positions of the points?
At some point they are closer to one another, pointing vertically. At some point they are like clusters. At some point they are separated individually.
Yep. So sometimes, yeah, thank you very much. That's great. So sometimes one of the things that happens when you ask people, so if you ask people, how many hours did you work last week? Which is what happened in this example. People are likely to give you estimates, right? So if you ask people who think that they don't work too many hours, they might say, oh, I work 40 hours, right? Or you might ask some people and they'll say, I work 100 hours, or I work 80 hours, or 90 hours, or approximately 70 hours, something. So essentially, you're looking at this question on the line arises because people are giving you estimates. And some people might have been nudged, like, oh, are you sure that's exactly the number? And then instead of saying 90, you might say, yeah, maybe 95, right? And that's what you have here. Or someone might say, oh, maybe 96 or something, maybe 84. So that's why you have this pattern. So some of what we might be seeing here is some degree of error in the way that the responses were collected. Okay. But we can look at the correlation here as well. It's negative 0.20. So this correlation is fairly straightforward. What do you conclude about this correlation coefficient? Like even if you hadn't seen the graph before and you saw a correlation of minus 0.20, what does the minus tell you? Anyone?
I think there is no correlation between mental health and number of hours worked by resident doctors.
Is that what the negative sign say? Is that what the negative sign says? What does the negative sign say?
Well, I think from the negative means that increases in one does not determine increases in the other.
You're getting there, yes, you're getting there, but there's one more thing that you have to clarify. Is it that increases in one does not affect increases in the other, or that increases in one are associated with what? Reductions in the other, okay?
Yeah.
So the negative sign, when you see a correlation score like this, it means that as one variable increases, say hours work increases, okay, then mental health score reduces, okay? So this is not a good one to see because if you also look at this, the number is 0.2, which says that there's no correlation, which is what Sherlock was getting at, that because it's very low, there's really no meaningful correlation. You might say that this is a weak correlation. But the negative sign, so there's two components of the correlation coefficient. One is the negative sign, and two is the number itself. And the number itself tells you how much correlation there is. Negative sign tells you the direction. And those are two pieces of information that are important to bear in mind. Any questions? Any questions, anyone? Yeah, go ahead.
R lab 4, is it the file?
That's the file, yes.
Okay, did you send that to us?
I did, yes.
Trying to search for it.
If you check the email that we sent this week that said this week in Stats 101, it's also in the email I sent today that is today in Stats 101. Someone said inverse relationship, correct. Inverse relationship is correct. So it shows that there's an inverse relationship when you see a negative sign in front of the correlation coefficient. Okay? But if there's no negative sign, it means that there is a positive relationship, whereas one increases, the other one also increases as well. Then if you look at the next thing, which is the value, then tells you the strength of the relationship, whether that relationship is strong or not, you know. And so who can tell us one challenge that we said that the correlation itself has, and why we need linear regression somehow? You remember from class, we said that there are some problems with correlation, or there's some things that correlation cannot do. And that's why we often need linear regression. Anyone? Maimuna, do you want to give it a shot?
No, I don't know.
Okay. Anyone else? Mahmouda, do you want to give it a shot?
Do I say correlation is limited in nature, sort of, in the sense that it cannot probably pick up cases that has to do with multiple variables?
Yes, excellent. When you have multiple variables involved, you cannot use a correlation. That's one. So if we back up, we said that to do a correlation, you need a continuous variable and a continuous variable. Two continuous variables, okay? And it doesn't matter which one is the exposure and the outcome, or which one is the predictor or the response variable. It doesn't matter, right, for correlation. But sometimes, right, you want to be able to examine the relationship between a predictor variable that is categorical, okay, with a continuous variable that is, with a response variable that is continuous. And in those cases, the correlation cannot be that. That's one. Two is that if there's confounding, and we talked about confounding in the previous class, right? If there's confounding and you want to include multiple other variables to adjust for them, then the correlation cannot do that. You need a regression to do that, and simple linear regression. Okay, so these are two key reasons, but there are other reasons. But those are two key reasons that I wanted to bear in mind. That one is that with a linear regression, at least one variable, the predictor variable, doesn't have to be continuous. With a correlation, both variables have to be continuous. The second point is that if you want to adjust for other variables, if you want to include other variables in the model, then you need a linear regression. You cannot use the correlation. Is that clear? Or does anybody have questions? I'm going to take it that there are no questions and move on. Okay. All right. So simple linear regression. So simple linear regression is, and so here, the points I was just talking about are right here. Okay. And you can go, when you go back to review this lab, you can also read this. It's essentially the same thing I was just saying. Okay. So simple linear regression is basically a correlation that, that goes further, that where we're able to standardize the relationship, we're able to change, we're able to include other variables if we want, and we're able to obtain what is called the beta coefficient. Okay? The coefficient that you obtain in a correlation is called a rho. It's called a rho. It's a correlation coefficient. That's right. This number is called a coefficient, correlation coefficient. But in regression, the estimates that we get are called the beta coefficients. Okay. So if you're going to run this, if we're going to do this analysis, essentially the same analysis we just looked at, we're going to do this in linear regression. This is how we write the code. So there's two ways to do linear regression in R. One of them is essentially just says LM, which is linear model, okay, you have one variable and you have the other. And you remember from last week, we said that there is this general form of writing code in R for looking at relationships where the response comes first and then the predictor. Okay? And it's the same thing from if we have the model equation. If you remember the model equation that we have looked at in class, where we have y equals beta 0 plus beta 1x. The y, which is the response variable or the dependent variable, comes first. And then you have this tilde. The tilde is, it looks like an approximate sign or something. And then you have the second variable, which is a predictor variable that you're using to explain this. So in this case, when you run this model and you specify the data where this is coming from, when you run this model, this is what you get. Okay? This is what you get. And the outcome here is the residuals. You remember we talked about the residuals? And this is just a presentation of what the minimum, the maximum, the orders of the residuals. But this is where the meat is at. So this is the intercept. If you remember, we talked about the intercept. The intercept is the number you get when x is 0, when the predictor variable is 0. Okay? That's what the intercept is. And so this is the intercept. And this is beta 1. So if you remember from class, we said y equals beta 0 plus beta 1x. And so this is beta 1. This is the magnitude. This beta 1 tells us that if you increase the number of hours worked by 1, okay? If you increase the number of hours worked by 1, the mental health score changes by this much. Okay? Let me take that again. If you increase the number of hours worked by 1, the mental health score changes by negative 0.03. This is a way to interpret a linear regression. This is the estimate is the most important thing. You can also look at the p-value, which is 0.0931 in this case, which is less than 0.05 and therefore is significant, right? Does anybody have any questions at this point? Or do you want me to go over this again? Anyone? Questions? You want me to go over it again? There's a very small class that gives you an opportunity to make sure that you leave this place today very clear on everything that we're going to look at. Okay, so don't postpone anything until later. Make sure that you understand all that we're doing, and that's why you've taken out time out of your schedule to do this. Okay. So this is one way that we do linear models.
So,
yes, please go ahead.
Hello. On the intercept, there's a probability there also.
This one.
And it's showing yes. So how do you interpret that?
Right. So you don't often like bother with it, but so let me back up and explain this. Like even if you had so this probability is a p-value, right? You know that?
Yes.
Okay. So essentially this intercept, you can be able to compare it to a population mean. So if you assume that there is a world of resident doctors at this hospital, you know, outside, even whether they are in your sample or not, but all the resident doctors at this hospital, right? The extent to which your population mean, okay, is related. The population mean of your mental health score, right, is related to the sample mean that you obtain. Remember when we talked about p-values, we said that the p-value tells you the extent to which your estimate is likely to be related to the population mean. Remember that? Yeah. So basically, the p-value here is giving you a sense of whether this estimate that you have calculated from your sample, whether it's likely to be correct or not. That's what this p-value is like, is telling you about. And this p-value, you get it from the standard error and the estimate itself. There's some way to calculate it. Okay? But we don't often bother with it if this is what we're interested in. Sometimes we're interested in the intercept in some types of analysis, right? Depending on the question we're trying to answer. But more often than not, we're interested in the beta estimate for hours work, you know, and this is the p-value we often interpret. Okay?
Okay.
Okay.